City College of New York. My name is Elijah Berry, and today, welcome to lecture number 7 of ordinary differential equations. Today, we're going to be doing power series. You might say, well, Saborno, isn't that a Calc 2 concept? And you would be correct. So let's go over some of the very common power series. Of course, we've got cos x is equal to 1 minus x squared over 2 plus x squared, x to the 4th over 4 factorial minus x to the 6 over 6 factorial, etc. Yeah, sine x is equal to x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7 over 7 factorial, dot, dot, dot. E to the x is 1, it should be 1 plus x squared over 2 plus x cubed over 6 plus x to the 4th over 24 and so on and so forth. So these are the common power series, and you can express any function that you want in terms of power series. But there are only so many functions you can express in terms of polynomials. There are only so many functions you can express in terms of polynomials, sines and cosines, and other trigonometric functions, inverses, and things in between like x to the half power, exponential functions. These, there are a lot of functions that can be made up of these, infinitely many of course, but they are not every single function. For example, take the Lambert W function. So, W of x, the Lambert W function, is the function such that W of x satisfies the equation so there is no way to write this out in terms of an ordinary function. In other words, even though we've got elementary functions in this definition, there's no way to explicitly write the Lambert W function in terms of any of these. So, however, we can still write a power series for the Lambert W function, but we'll get to that later. So for now, today, we're just going to get used to actually using these. So we're going to be solving equations that we already know how to solve with power series. For example, this equation, y prime plus 2y equals 0. You definitely know how to solve this one, right? In fact, this is the simplest class of equation, a separable equation. So, it's as easy as pie to separate this thing. Get 1 over y dy equal to minus 2 dx. So, integrating on both sides, you get minus 2x plus c is equal to ln y. Or in other words, y is e to the minus 2x times some constant. So y is c e to the minus 2x. Plugging it back in just to verify, y prime is minus 2c e to the minus 2x. So we get minus 2c e to the minus 2x plus 2c e to the minus 2x equals 0. Sounds pretty verifiable. So we know that we solved this equation pretty easily. But now we're going to introduce a power series element. How are we going to do that? Well, take y to be some power series. A power series can express anything you want. That's anything you want. That's what a Taylor series is. But we haven't solved it using power series yet. So we can make any function we want out of power series. That's what a Taylor series is for. So let y be equal to the infinite sum c sub n x to the n from n equals 1 to infinity. So what does this give us? C0 x to the 0 plus C1 x to the 1 plus C2 x to the 2, and so on and so forth forever. Now, what happens if we take y prime? Well, it should be pretty easy to tell from the sigma notation. All we have to do is take the derivative of every single term, which, since the derivative of two functions is equal to the sum of their derivatives individually, since this is true, all we have to do is take the derivative of that individual function. So here, we can just have Cn, and by the power rule, nx to the n minus 1, right? So, how would we write that? Well, as C0 x to the minus 1, but wait a second, we can't do that anymore. That is lost to history because it's a constant. So when we take the derivative, it becomes 0. By the way, I just realized I should add this. Sorry. So as soon as we take the derivative, since we're losing one term, this would actually no longer be 0. This would be 1. So we get C1 times x to the 1 minus 1, 0. All right, now let's move forward. We get plus C2 times 2x to the minus, to the positive, to the first, plus 3C3 x squared plus 4C4 x cubed, and so on and so forth. So now is the effort begins to try and find a pattern. So we get y prime is equal to the sum of n Cn x to the n minus 1. All right, and then we have 2y is equal to the sum of n Cn, wait no, just Cn xn. All right, so now all we have to do is add these guys up. So we get the sum of this plus this has to be equal to 0. Has to be. So now, how will that have to work? Well, let's take a look at the first few sums of this and see if we can get a hang of how it works. So, first sum we get is just C0 x0 times 2. And then the second sum we get is 2 C1 x1 plus, C1, plus C1 x to the 0. All right, and then the third term we get is 2 C2 x to the 2 plus 2 C2 x to the 1. And then the next term we get is 2 C3 x to the 3 plus, all right, now we can start getting the hang of it, 3 C3 x to the 2. Then we get 2 C4 x to the 4 plus 4 C4 x to the 3, and so on and so forth. Now it's more beneficial to look at the individual terms by their polynomials. What do I mean by that? Well, we factor out x0 and we get 2 C0 plus C1. That's our constant term. Factor out x1 and we get 2 C1 plus 2 C2. Okay, we factor out x2, x squared, and we get 2 C2 plus 3 C3. Then factor out x cubed, then we get 2c3 plus 4c4, and so on and so forth. And the thing is, every single one of these terms has to add up to 0. So what do? Well, we just act naive and we try to solve. 2c0 plus c1 is equal to 0. So that gives us c1 is equal to minus 2c0. Okay, then 2c1 plus 2c2 is equal to 0. That gives us that c2 is equal to minus c1, which is equal to 2c0. Then we get 2c2 plus 3c3 is equal to 0. So we get that 3c3 is equal to minus 2c2. So then, what's the overall relation between Cn and Cn plus 1? Well, what I'm gathering from here is that Cn is equal to minus 2 Cn plus 1. All right, pretty simple, huh? Pretty simple to follow, right? Never mind, it's 2Cn minus 1. So for example, we have 3C3 matches up, minus 2C2 matches up. 2C1 equals minus 2C2, or if we wanted to rewrite that, we get 2C2 is minus 2C1. Yeah, this equation works out. Or if we want to go forward and not backwards, we want to use n plus 1, Cn plus 1 is equal to minus 2 Cn. Alright, cool. So now we have that Cn plus 1 is equal to minus 2 over n plus 1 times Cn. So what does that mean? Well, in essence, it means we start off with some value C0. Then we multiply it by some ratio, in this case, minus 2 over 1. Then we multiply that ratio by another ratio, minus 2 over 1 times minus 2 over 2. Then we multiply that one by another ratio, minus 2 over 1 times minus 2 over 2 times minus 2 over 3. So then, what do we get? Well, we get that Cn, in terms of C0, tends to be equal to minus 2 to the nth power divided by n factorial. Seems pretty obvious, right? So, what do we glean from that information? Well, if we look back at our actual solution, we'll notice that it's c e to the minus 2x, right? What's the Taylor series of e to the x? Like we mentioned before, it's the sum of 1 divided, not 1 divided by, was it? Let's take a look. Yeah. 1 divided by n factorial. So now, what's happening here? Well, of course, we're multiplying by x to the n. And so, once we add that factor of minus 2x in, we're plugging in this over here. This is the Taylor series for c e to the minus 2x. Of course, if you really want to, you can also add the constant, but you don't have to. We'll just ignore it right now. So then, we get minus 2 to the n over n factorial times x to the n. So, in other words, this is the exact same thing that we saw over here. So, we can show that that solution that we ordinarily got and this solution are the exact same thing. But you might say, oh my goodness, Adorno, that took so long. That took a literal eternity, while separation of variables takes 2 seconds. So why do this? Well, the thing is, separation of variables, it doesn't always work. Undetermined coefficients doesn't always work. variation of parameters integral may be impossible or too complicated for you to figure out. So, your last resort in ordinary differential equations, when you can't figure out what to do, is this. So, next time, we're going to figure out how to use this technique with functions that we actually don't know how to specify using elementary functions. Here, we managed to specify it using e to the minus 2x. That's just a combination of an exponential function with a little coefficient up top. Extremely elementary. But next time, we're going to see how to express functions in terms of power series that we weren't able to express at all before. Thank you.
What do you see?
Sand.
Imagine if we could look so closely, we could see each grain, each particle. You see, there are patterns in everything.
Integrals, infinite series.
I've never seen anything like them. From an Indian...